I'm really excited to be here to introduce our next speaker. My name is Nicole Seiberlich, and I am an associate professor in the Department of Radiology at the University of Michigan. And I'm really excited to introduce Saiprasad Ravishankar, who is our next speaker. Sai received his Bachelor's of Technology in Electrical Engineering from the Indian Institute of Technology, Madras in 2008. And he then went on to the University of Illinois at Urbana-Champaign, receiving both his MS and his PhD degrees in electrical and computer engineering. After he received his PhD, Sai became an adjunct lecturer in the Department of Electrical and Computer Engineering and a postdoctoral research associate in the Coordinated Science Laboratory at the University of Illinois. Starting in 2015, he was a postdoc in the Department of Electrical Engineering and Computer Science at the University of Michigan here in Ann Arbor, where I am sitting. And he then went on to the theoretical division at Los Alamos National Laboratory as a postdoc research associate. Currently, Sai is an assistant professor in the departments of computational mathematics, science and engineering, and also biomedical engineering at Michigan State University. And he's the leader of the group Signals, Learning, and Imaging, that's the SLIM group. And his research interests include signal and image processing, computational and biomedical imaging, data-driven systems, machine learning, signal modeling, inverse problems. I think you get the picture. So today we are really lucky to have Sai to speak about medical imaging perspective on inverse imaging techniques and machine learning in medical imaging. So Sai, I'm going to hand the stage over to you.
Thanks, Nicole. That was a very generous introduction, and I'm happy to present in this wonderful seminar series. And I would like to thank the organizers for inviting me. And this talk is going to be focused on machine learning for medical image reconstruction. And Max did a great job explaining, doing part of the explaining for the what image reconstruction is, what image problems are, and sort of why they are non-trivial, and why you need more sophisticated algorithms. With medical imaging, also we typically do not directly observe the sort of the anatomies that we are interested in, but rather we observe indirect measurements in say CT or in MRI or in other imaging systems. We observe indirect measurements, and then we have to sort of go back and infer the object or the tissue or the whatever the image that you're interested in from those measurements in the scanner. And that process involves sort of the image reconstruction or image inversion. And that is non-trivial for a variety of reasons, because the data that is collected in the scanners is often corrupted or limited, or there are various artifacts in the data, or the imaging process, the forward model, is sort of not perfectly characterized. So a lot of issues may prevent sort of doing the image reconstruction in a straightforward way. Of course, the early methods for medical image reconstruction involve sort of doing more straightforward analytical reconstructions. And in MRI, for example, gridding that Max talked about has been used for doing non-uniform Fourier reconstructions. And in CT, for example, filter backprojection was a technique that had been used for a long time. And but more recently, there has been a trend to sort of bring in machine learning to solve these kinds of problems for doing image reconstruction in CT, in MRI, PET, SPECT, in a lot of these systems. And so that's going to be the main focus of my talk. And I'll take you through sort of a few works from myself and collaborators in this domain. And so starting with this approach called PWLS Ultra. And this might fall into the category of sort of shallow learning methods. That is, we try to learn sort of a sparsifying model for images from a data set of normal dose or regular dose CT images. And then we sort of use this model to form a data-driven regularizer for iterative reconstruction. And so that'll be the first part of the talk. And then I'll move on to sort of bringing in deep learning. So we have this sort of unified framework where we kind of can bring in physics-based forward models, statistical models of noise and the measurements, and together with different kinds of data-driven models, like shallow models, like the union of learned transforms, or deep neural network models, and sort of in a common mathematical framework for doing image reconstruction. And most of this will be focused on CT, and I'll also show some MRI right at the end. So I have sort of a pipeline over here that kind of roughly indicates the kind of methods we'll be covering. Usually there is a training phase where we use a data set of images or obtained from patients or other kinds of objects, depending on the application. And then we sort of learn priors or models that can be then incorporated at image reconstruction time inside of algorithms. And sometimes these models can also be updated while you're performing image reconstruction so that it adapts to the object you're imaging directly. So there are a few different flavors possible of how the learning can be done. And without further ado, let's get to sort of the first approach. So before I move on, before I introduce the method, I want to motivate the application. So the application here is low-dose CT reconstruction. And the goal is to sort of allow us to perform CT scans by exposing patients to significantly lower radiation, X-ray radiation, than they would be normally exposed to. And we would like to do that while still maintaining high quality of images that are reconstructed so that we don't lose image quality in response to reducing the X-ray dose. And so there's a trade-off. So a lot of algorithms exist in X-ray computed tomography for performing image reconstruction from those measurements. Filter back projection is sort of an analytical reconstruction method. It's very cheap to apply. But if you are doing low-dose CT imaging, then it produces undesirable artifacts in the images. Model-based or statistical reconstruction methods are kind of more popular, and they bring together sort of the forward models, the measurement, sort of the forward model of the imaging process, the statistical models of noise, and often simple priors of the underlying object to perform reconstruction. Newer approaches in the model-based framework tend to learn the object priors. So learn these priors of what the objects are from data sets of images, and then use them in reconstruction. So that'll be the focus of the first part of what I'm talking about. And so here's an example comparing like a conventional approach for CT reconstruction, which is filtered back projection, and to sort of the second class of methods, the statistical approaches that I mentioned. And so clearly we can see that the statistical reconstruction methods produce much less noisier images, and the features of these images, the anatomical features are visible much more clearly than in the in sort of the analytical, the simple filter back projection reconstruction. And we are interested in sort of improving these model-based or statistical reconstruction methods by learning priors of the objects. So the prior that I'll be interested in, that I'll be talking about, is this sparsifying transform prior. So here the assumption is that we have an image or a signal X, and then there is an operator omega, which we call the sparsifying operator. The model is that when we apply this operator to the signal, we get something that's approximately sparse. So the Z has many zeros, and then eta is like a small approximation or modeling error. This should remind you of things like the wavelet transform or the discrete cosine transform or things like that for images that have been used in a lot of applications. So it is well known that if you take an image and apply the wavelet transform to it, you get something, a representation that looks very sparse with a lot of zeros or some elements close to zero. And this has been exploited in image compression, in image denoising, in compressed sensing, and in a lot of different applications. So given such an image, a signal, and a transform, we can sort of get this sort of sparse approximation by transforming the signal and sort of setting the smallest elements to zero. And then this sort of sparse representation is then used in image denoising and other algorithms. And our goal is to sort of learn these transforms rather than using off-the-shelf transformations. We want to learn them from data. And in particular, we'll be looking at learning a union of sparsifying transforms, and the learning will be done based on image patches. So let me introduce what image patches are. So I'm just zooming in. So this is sort of a CT phantom image where I'm showing patches. These are the red, the yellow, the green, and the blue boxes. And sort of the content in them represents the patch. And depending on which patch or which portion of the image we are looking at, the features of the patch may be quite different. They may correspond to the bone, the soft tissues, or the blood vessels, other kinds of features. So the idea with this union of sparsifying transforms model is that we would like to somehow group these patches from different regions into different classes. And there's a transform for each class that best sparsifies the patches in that class. So similar to what I showed here, that instead of a single transform omega, there is a collection of transforms, and each of them is suitable for a class of patches or features. And because we do not know a priori what is this grouping of the patches from an image, we have to do this sort of automatically. And so here's sort of an approach where we essentially learn this union of transforms from training patches. So assuming we have a collection of training patches denoted as xi, the goal here is to learn a collection of transforms denoted as omega k, and to sort of group these patches into one of capital K different classes. And so the idea is that if the patch xi belongs to the kth class, there's a transform omega k, which can be applied to the patch to give a sort of a sparse representation. The zi is a sparse approximation, and we would like to minimize this error while promoting sparsity of zi through the L0 norm that counts the number of non-zeros in that vector. And here we also have some regularizers which are used to enforce properties on transforms that meaningful or interesting properties we would like to see in the transforms. And this is sort of an optimization problem where we are trying to learn a grouping of the patches. We are given these training patches. We would like to learn a grouping characterized by the set CK. So CK denotes the indices of patches in the kth class. And we would like to learn this grouping and learn the transforms in each group or class of patches. And so this is sort of a non-convex optimization problem, but we have in the past proposed algorithms that can efficiently solve this problem by alternating between different variables, between optimizing different variables. So I won't get into the details of how do you learn the transforms, but I want to talk about how can we then, if we are able to learn them, how do you use them to perform image reconstruction? So image reconstruction in a lot of different applications like MRI, CT, PET, SPECT, and so on, can be posed often posed as an optimization problem, where the goal is to reconstruct the image X from the measurements in the scanner Y. And these measurements are somehow related to the image through this forward model or sensing matrix A. And the first term in this optimization essentially is called a data fidelity term. It measures sort of how close the measurements are to the image that's reconstructed once it's been transformed to the measurement space. And depending on the statistics of the measurements and the noise, you may have different kinds of terms here. So the weighted least squares penalty is often used in CT, or you can have a least squares penalty or other kinds of penalties that sort of, you can think of them as log likelihood terms. And then often there's a regularizer as well. This regularizer allows us to enforce prior assumptions of the image that we are trying to reconstruct, such as the image being smooth or sparse in some domain, or sort of other properties that we sort of know a priori that the image satisfies. And by solving this combination of the data fidelity term and regularizer, we hope to reconstruct the images. And compared to conventional methods where this regularizer was sort of mathematically designed, we are interested in using data-driven regularizers. So that's sort of what's happening here, the regularizer is coming with this union of learned transforms. So remember, what I said previously was that if you have a data set of image patches, we can sort of use that to learn this union of transforms or collection of transforms. And there's an algorithm that kind of does the learning given these training patches. Now, once these transforms have been learned, we can plug them to form a regularizer for image reconstruction. And that regularizer is shown over here, where essentially these transforms are being applied to patches of the image that you're trying to reconstruct. So those are the PJX, the patches of the image X. And this regularizer has a minimization over the cluster memberships and these sparse coefficients. So because the image is being reconstructed, we have to determine which patches belong to which transforms or which classes sort of automatically while doing the reconstruction. So this sort of becomes this joint optimization problem. What we are given are the measurements Y, and we know this forward operator A. And we know these transforms omega 1 through omega capital K because we learned them from a data set. But then we have to optimize for these cluster memberships and the image itself. Now, we can do this by alternating minimization, where essentially in one step, we fix the cluster memberships or the patches and these sparse feature vectors or sparse representations. And we optimize for the image in the problem. And that becomes this sort of quadratic optimization problem, which can be solved relatively efficiently using algorithms such as the relaxed linearized augmented Lagrangian method with ordered subsets. It's a pretty long name, but that's a recent method. And we used it because it allows solving this problem very rapidly with relatively few forward and back projections. That means applying A or A transpose inside of the algorithm, which tends to be for CT quite expensive. So once we solve this quadratic problem, we can then go to sort of the other step, which is you fix the image and then you optimize for the cluster memberships or the class memberships of the patches and these sparse coefficient vectors. And this optimization is non-convex, but we can sort of get rid of this ZJ variable by replacing it with a closed form expression, which is just a thresholded version of the transform patch. And once we do that, this problem becomes relatively straightforward. We just need to evaluate this loss function that I'm showing here, which is evaluating how good is each of the transform at sparsifying a specific patch. And then we pick the transform that gives the smallest value of this cost function. And so that's the transform to which you group the patch, the jth patch, let's say. And sort of this has to be done for all the patches. Then you sort of are able to group the patches into these K classes. And then these coefficients Zj are obtained by just applying the corresponding transform that you group the patch into, applying it to the patch and thresholding the result. Hot thresholding, which is basically it sets elements below gamma to 0, and it doesn't do anything to other elements of the vector. So essentially, this alternating algorithm can be run until convergence, and so that we get a reasonable solution or an optimum of this problem. Now, I want to show results for images. So we sort of have performed experiments on phantoms as well as real patient data. And so we did the training of this union of transforms on the XCAD phantom. So this is a 3-dimensional phantom, and we use sort of a portion of the volume to perform the training. So we used patches, image patches that were 3-dimensional, 8 by 8 by 8 patches, and there were like 1.5 million of them that we extracted from a portion of the volume, and we used that to learn this union of transforms. And then we used it to perform reconstruction on a different portion of the XCAD phantom volume. So for that testing part of the XCAD phantom, we generated the sinogram or the CT measurements using a cone beam CT geometry. And then we also simulated noise in the measurements using a Poisson plus Gaussian noise model. And then we performed reconstruction with different approaches. We used the filter back projection, which I mentioned earlier on, which is a conventional approach. And then we performed this sort of iterative reconstruction with sort of what's called an edge preserving regularizer. This kind of assumes that the image is sort of sparse in a gradient domain. So there's no learning involved. And also we used the union of learned transforms, that's the ultra scheme, to form the regularizer. So we did a few comparisons. To test the generalizability of the transforms learned on the XCAD phantom, we also tested those on with a chest CT scan to see how well they do on a completely different scan. So here are results with the XCAD phantom, where we can see, so the top and bottom rows denote 2 different X-ray dose levels on which the imaging, at which reconstruction was performed. And the lower the dose, the worse the FTK or the filter back projection reconstruction gets. You see more and more artifacts, streak artifacts with the conventional approach. Both of these iterative reconstruction techniques do a lot better than FTK, but then EP sort of still has a lot of noise. Let me zoom in a little bit more. So EP still has noise in the reconstruction, but with the union of learned transforms, we not only remove the noise, but we can also preserve the finer details better or reconstruct them better. And along with these reconstructions, we can kind of get interpretable representations of what we have learned. And so this is kind of showing that because we are in the process, clustering or grouping the patches of the image into these classes. So here we have 5 different classes, and because every pixel in this 3-dimensional volume is covered by many overlapping patches, we can sort of cluster every pixel into one of these classes by looking at the patches overlapping it, and then sort of doing a majority vote over their class memberships. And so this is sort of showing a grouping of the pixels in a certain slice in the 3D volume, and we can see that the bones have been grouped into a certain class, the soft tissues into another, and different kinds of edges have been grouped into the other classes. Along with these classes, let's look at the transforms. So these were pre-learned on the XCAD Phantom, and these are 3-dimensional transforms. I'm showing a slice, a 2D slice through them, and we can see that the features in these transforms correspond to the kind of features that are grouped into that class in the reconstruction. So this is sort of allows us to interpret what the learned model is doing. And the code for this work is on GitHub, as well as for all the other works that I'll present. And so the last part I want to mention is we took these transforms learned on the XCAD Phantom, and we applied it to a chest CT scan. And so again, we have the filter back projection reconstruction, the EP reconstruction, where there's no learning involved, but still it's an iterative method. And then Ultra uses the union of learned transforms. And again, we see that the noise is removed better, as well as the image features are retained more clearly in the Ultra reconstruction. What this suggests is that we may not need closely matched training data sets for this sort of union of learned transforms to work well. And also we can learn on relatively small data sets, like we used a portion of the XCAD Phantom to train the transforms, and they still do well on very different data. Okay, so now you might be thinking like, well, how about deep learning? So sure, deep learning has gained a lot of interest in recent years and in our imagination in classification, speech recognition, image analysis, image restoration, and image reconstruction as well. And in deep learning, essentially, the relationship between an input, this could be a corrupted image, and an output such as a classification result or a denoised version of the image, this relationship is represented through multiple layers or stages of functions or transformations. And typically the parameters of this mapping, of this multi-stage or multi-layer mapping, are learned from data sets of input and output pairs. And this sort of deep learning can be done in a variety of ways. So there's something called image domain learning, where a network is learned to denoise images in sort of the image domain. So this is sort of an illustration for CT. So assuming that we get sort of the CT measurements, which is called the sinogram, we can perform a conventional reconstruction, filter back projection. And if we sort of had obtained low dose measurements, the filter back projection image would look very noisy with all these streak artifacts. Now, with image domain learning, we can learn or train a neural network to remove the artifacts or map this corrupted image to sort of a clean looking image. This clean looking image must have been collected at a much higher X-ray dose than this one, because so otherwise, we wouldn't know how to generate the output based on the input. So typically what is done is you collect 2 sets of measurements, one at regular dose or normal dose and one at low dose. And then you can sort of learn a mapping that goes from one reconstruction to the next. And so as a counterpart of image domain learning, there's sort of sensor domain learning. Here, what happens is that we take the sinogram, which may be corrupted or not noisy, and then we learn a network to map it to sort of a much higher quality measurement or sinogram. And then we follow it up with just a simple analytical reconstruction. In this case, because the sinogram is of a much higher quality, you get an image that's a lot better, even with filter back projection. Now, so these 2 methods are kind of similar. The network is learned in the sensor domain or in the image domain. The third method that people know about is the auto map, which sort of eliminates this analytical reconstruction and just learns a network that goes from the measurements to the image. The drawback of this approach is that often you need like a fully connected layer in the AutoMap network, and that makes it a lot harder to or expensive to train and to store. The methods that we are interested in are these hybrid domain methods, where essentially the network is sort of, the learning of the network is coupled together with sort of a forward model of the imaging process. The imaging, the forward models, the statistics of the noise, etc., are sort of incorporated into how the network is trained. And with that summary, let me sort of again rephrase some of the methods we've seen until now. So we looked at sort of these unsupervised learning-based iterative reconstruction methods, where basically we solved an optimization problem that incorporated the imaging physics, the statistics of the noise, and also some learned prior. So we could learn these union of transforms from very limited images or slices and incorporate them into the reconstruction. And they had relatively good generalization properties. But the con is that the reconstruction is very expensive because you have to run many iterations of an algorithm. With this deep learning-based methods, if you're doing image domain learning, for example, you can get strong denoising capability, and the method is pretty fast because you just have to use a feed-forward neural network and get a reconstruction. But these methods often require large training sets, and otherwise you might run into overfitting issues. And that some of you might have heard about is that it does create a lot of potential problems when you're testing these networks. So what we propose is sort of a way to bring together the advantages of different kinds of data-driven models in this sort of unified, supervised, unsupervised scheme. And so let me sort of build up to what this method is. So let's start with just the image domain deep reconstruction networks or deep denoising networks. So this is where we have a set of measurements Y, and we may use an analytical reconstruction algorithm like FBP, filter backprojection. And then we sort of learn a neural network that sort of removes the artifacts in that reconstruction. So after the network is applied and the artifacts are removed, you get something, a reconstruction that's still parameterized by the network. And contrast this with sort of a model-based or iterative statistical reconstruction method where we have sort of this data fidelity term, a regularize, and we minimize it using an iterative algorithm. And so in this framework, we can also add in a network-based regularizer. So here what we are saying is that I want my image to be fairly close to the output of the denoising output of a network. And so once you plug this sort of output of the network as part of the regularizer, we can solve this reconstruction formulation in a sort of a model-based way. And then we get a reconstruction that is sort of more consistent with the forward model, the regularizer, and so on. And then you can take this and maybe it still has some artifacts, so you can sort of learn a network to again denoise it further. And once it's denoised further, you can put it back into the regularizer and sort of make it more model consistent and so on. So this sort of leads to this iterative process where essentially we take an image, it is passed through a network that removes the artifacts, and then that is plugged into this model-based reconstruction formulation, and we minimize this cost function again to get a new reconstruction, and we repeat the process. And so that looks fairly complicated, but it's sort of just bringing together the two different reconstruction paradigms that I talked about. One is the deep learning-based denoising, and sort of the other is the iterative reconstruction by optimizing this model-based loss function. Now, if you ran this algorithm to convergence, you get sort of, this is like a fixed point iteration. If you ran it to convergence, you get a fixed point condition that looks like this. Essentially, this is saying, I take my reconstruction and pass it through this complicated mapping represented by this minimization, and then I get back the reconstruction. So that's when the fixed point iteration is said to have converged. So the fixed point iteration, let me clarify, is an algorithm that can be used to find a solution to this fixed point condition. This fixed point condition sort of, I can say, is something that brings together all the different models that we are interested in. It brings together sort of the physics, the physics-based forward model, the noise models, the regularizers. These regularizers could be like a union of learned transforms, edge-preserving regularizer, whatnot, along with sort of a learned neural network as well. And the way we will learn this network, so instead of using an ad hoc network, inside of these fixed point iterations, we can learn networks in each iteration that sort of maps the images to sort of denoised versions, things that are close to the ground truth images that we are interested in. So the training proceeds as follows. So every iteration, fixed point iteration, we will train a network so that it takes the the image from the previous iteration, so this image, and so it tries to map it to high quality images, which are represented by this X star. Once you train the network, you have to sort of plug it in to the minimization problem, and then we solve this minimization and get a new set of images, and then we train a network again to denoise those images. So sort of we alternate between these two steps, and essentially this just corresponds to the same fixed point iteration. It's just that we are learning the network now. You can also view this from other mathematical perspectives, like the training can be seen as a heuristic for solving a bi-level machine learning problem. So I won't get into the details of that. That can be found in our paper. But once you train these networks, you can then basically apply them on to reconstruct other images. And that basically involves going through the iteration pipeline for the fixed point iteration. So basically get a reconstruction, pass it through a network, the corresponding network, solve the optimization, and then repeat the process, right? So that can be also seen as this pipeline where we start with an initial reconstruction that might have a lot of artifacts like the FPP reconstruction, and then we denoise it with the network, and then we have optimize the model-based loss function and repeat the process. So in order to test this approach, we use different architectures for the supervised and the unsupervised part. For the supervised network, we used FPP ConNet and WaveResNet, which have been used in CT reconstruction. For the unsupervised part, we use like weighted least squares for the data fidelity term, and then for the regularizer, this R of X term, we used both an edge-preserving regularizer and a union of learned transforms. And we experimented with the Mayo Clinic dataset, which we simulated 2D fan beam CT projections with Poisson and Gaussian noise, and we used a subset of the Mayo dataset for training and a subset for testing. And here we are showing sort of the root mean square error on the testing dataset for different methods. So it's shown using box plots. And the main thing I would conclude, or I would point you to here, is that if you look at the box plots for these super methods that sort of bring together the deep neural networks and sort of the edge preserving on the ultra regularization, those box plots have much smaller spread, and also the median values of the errors are much lower compared to the either the deep network methods by themselves or the iterative methods by themselves. And here we are showing sort of more numerical metrics, RMSE, signal to noise ratio, and SSIM for different methods. And again, combining together the deep neural networks and either the edge preserving regularizer or the ultra regularizer gives you significant benefits over just using these methods by themselves. And in particular, using a union of learned transforms gives a better performance than using the edge preserving regularizer. And there are more results in our paper, and I want to show some images. So here we are showing visualizing low-dose CT reconstructions with different methods. The edge-preserving regularizer results are kind of blurry, and the ultra result seems to be sharper. This is with the union of learned transforms that I talked about at the beginning. And if you use the deep neural network like the WaveResNet, sometimes it introduces spurious artifacts. But with this ultra scheme, which brings together both the WaveResNet and EP or ultra, you can get much sharper images, and the features are reconstructed better, and the RMSEs are lower. And here we are sort of showing this similar results, but we replace the network with the FPP ConNet architecture. And here we see that FPP ConNet can produce some spurious looking artifacts in the image. And those are corrected once we sort of use our super framework. And here we are just showing convergence of the image of the root mean square error over iterations, or how many fixed point iterations you run. And we see that basically the RMSE, the median RMSE, which is the red line, it seems to converge in a few iterations. So you may not need to run this for many iterations to get a good enough image. And if you look closer at how the images look like, the first several iterations of the algorithm, mostly the noise is removed. And in the later iterations, the root mean square error changes very little, but mostly the image gets a little sharper. So that may be the trade-off we need to play with in sort of choosing how many iterations we run to get the quality that we want. So the last thing I want to very quickly mention is that we've also applied this for MRI. And in MRI, sort of the architecture we tried out is slightly different. So we sort of use this blind plus supervised architecture. The supervised, so this is just a single shot pipeline with just two modules, a blind module and a supervised module. We could potentially repeat it several times, like I showed for CT, but we found that even using just this combination seems to work well. The supervised module is sort of a deep unrolled network, so it has a CNN denoiser, and it also has sort of a regularized image update where the output of the denoiser is enforced to be consistent with the MRI measurements. And this here is sort of the blind reconstruction module. I won't get too much into the details, but this is an approach that sort of allows performing image reconstruction and also learning dictionaries for the underlying images simultaneously. And that's an iterative algorithm that was used to sort of create an initial reconstruction, and that was improved further by the supervised deep neural network. So what we found is that this combination of bringing together the blind learning method and the supervised network had a lot of robustness. So if you reduce the training set, the size of the training set, this is using the fast MRI multi-coil ME data set. So if we had much fewer training signals to learn the network in the blind plus supervised architecture, the performance was a lot better compared to the strict supervised scheme, which is just this part of the architecture without the blind module. And and also some images here showing that this is sort of the BLIPS reconstruction that combines together both the blind learning scheme and the supervised network. So the image features are sharper than what you get with just a strictly supervised network. And if you look at this architecture, I said there's the blind learning module and there's also the supervised module. The first module kind of produces an image that gets most of the details, but it's still a little blurry. And if you look at what component is added back by the supervised network, that's shown over here. So the supervised network adds back a significant amount of detail that it was able to learn on sort of in a population adaptive manner from the data set, from the training data set. So that's about it. So I would like to summarize by saying that I introduced method for learning a union of transforms from a small data set of images, and this could be used to form regularizers for low-dose CT reconstruction. And then I proposed this sort of unified framework where we could bring together supervised deep learning and sort of unsupervised learning or mathematical priors and physics-based models or statistical models, and in sort of a common framework or a combined framework where they complement each other and provide more improved or effective reconstruction. And I would like to say that there's still a lot of work that can be done in this domain in terms of building better algorithms that learn regularizers or learn priors for different applications, and also characterizing what kind of biases are introduced by these learned models. There's still a lot of understanding that needs to go in there, and we hope to work on that going forward. And with that, I would like to thank some of my collaborators at different institutions, and thank you for your attention.
Great, thank you, Sai, for that great talk. So we can get started with a question. What is the main driver of using learned models for image reconstruction? Is it reduced image reconstruction time, higher precision, resolution?
Excellent question. I would say it's often a combination of both of those things. We would like to improve the precision or accuracy of the image quality while performing reconstruction, and we are also, there's also interest in reducing the reconstruction time. But there is a trade-off involved, with some of the methods that I talked about earlier, where you're sort of learning a denoiser in the image domain or in the sensor domain. This might be very easy to very quick in giving a reconstruction, but the quality of the reconstruction there may not be as good as you desire, because you're leaving off a lot of the information that we know about the imaging process. On the other hand, with these hybrid learning methods, we tend to get better reconstruction quality, but then it's also a little slower. So I would say kind of there's a trade-off, and it depends on the application and what the target is. If the goal is to get something really, really quick, then maybe it's fine to use sort of just an image domain denoiser or a sensor domain denoiser. If not, or even or I guess even filter back projection or the non-uniform Fourier transform that Max talked about, they would give you relatively quick reconstructions too. But then the idea with machine learning is we want to use all the information or data sets that we have collected in the past and that are also being collected in an ongoing basis and sort of leverage that information to improve image quality. But within sort of the machine learning methods, I think there is also a trade-off depending on the complexity of the model. Which model would you like to use in terms of there would be a trade-off in terms of reconstruction time versus image quality.
Always on my mind when we're talking about patches, because I do a lot of MRI reconstruction, but not with patches. And so I'm curious about the underlying assumption of working with these patches. Is it that there's going to be some finite number of patch appearances in those images? Because that assumption makes me a little nervous, to think that there's going to be just maybe a large but a defined number of patches. And I suppose it depends on the patch size as well, but you could imagine the extreme case of your patch being the entire image, right? Mm-hmm. Clearly that's not going to be appearing more than once if you're looking at medical images, for instance. But can you talk about that, that big assumption that happens when you're using these patch-based reconstruction techniques?
Right. I would say in sort of the traditional, sort of the earlier method that I talked about with where we were learning this union of transforms, the using patches is sort of also necessary from a computational perspective, because if we were trying to learn a transform that worked on the entire image, that's a very, very high dimensional transform, and very expensive to learn or to store and whatnot. So often, at least with the transform models and so on, the learning is done on smaller patches. The advantage of that is that a single image can give you a lot of patches. So instead of if you're doing it at the level of the image, you may need to collect like 1 million images to train a model. But with patches, you can take a single image and get hundreds of thousands of patches from a single image if you allow the patches to overlap. So that kind of allows you to overcome limitations, like if you didn't have a lot of images from which you could learn the model. And this also holds with deep learning methods. So in deep learning methods that some of them in the literature, as well as things that we have worked on, we found that if we are limited in the amount of training data, then just using a patch-based method kind of allows us to create a lot bigger training set, because we are extracting all kinds of patches from the images that we have. And I mean, there's also the other issue that if you are doing patch-based processing, that the computation may be higher, because you need to sort of process a lot of different patches independently and then sort of aggregate them back together. In terms of, are there any drawbacks to using patches versus the full image? I think that's a very interesting question. I think when we are working with patches, the smaller the patches, we are looking at very local information that we are trying to leverage. Whereas the larger the patches, then we are also kind of getting global information, things that kind of across the whole image maybe. So then maybe there's some trade-off in sort of what level of features can be extracted depending on the size of the patch. I hope that touches, I think this is a kind of a big question covering, with lots of different dimensions to it.
Yeah, I think there is another question. What is your view on forcing machine learning to learn physics? So for instance, transforms that we know about, as opposed to taking the physics out analytically, if it's possible?
That is a very good question. So, I mean, there has been a lot of talk and work on learning the physics. I can say from our experience that if you're trying to learn the physics, but you have sort of a data set on which you're training it, you might end up learning more like the properties of that data set rather than something that's as general as physics. So I think in order to really learn physics, we have to be able to learn at a much, much larger scale on data that is very representative of the universe, where the physical model holds, to learn something meaningful. Otherwise, machine learning that we have, neural networks, they are very good at capturing the intricacies of a specific data set. And then sort of that's no longer physics. So I think that's an interesting question. But in terms of like in CT or MRI, I think we are far from where we can say like we can use machine learning to just learn the physics. Or maybe Nicole has some. I see Nicole nodding her head. Maybe you have alternative thoughts on that.
But we love using machine learning to learn the physics because MR physics can be a little messy, but we know what it is. I think the trickier part of medical imaging is that the biology starts to come in too, and that gets really messy. So we have kind of the clean version of the physics plus the messy biology that's involved, and that's what, in my opinion, makes it a little tricky to rely on machine learning. But to get a neural network to do physics alone, I think is pretty. We can do a lot with that, I think.
Well, I guess the question is like, how do we verify that the model has truly learned physics, right? And versus whatever it's been learned, is it corrupted by the features of the data set?
Yeah, so we in our group we use we'll generate signals using known physics. We can train our model using just physics basically. So we have like neural networks that just recapitulate the block equations or whatever for MRI, and then we're pretty sure that we just have the physics there, and anything else that's kind of funny might cause a problem when we go back to try to use our trained network to do the reconstruction. But we can just get the physics. I agree. If you're working with real images, then you might have other confounding factors. But I think neural networks are really good at physics. It's pretty easy. There's another question from the audience, and the question is, when would you need to retrain models for your approaches?
Right. So I think that's a very valid question. Like, if I train the model on a data set, and then how do I know for whatever the image that's being scanned, is this model appropriate? And if it's not, is there any backup? Like, does retraining need to be performed, and how did it be performed? So we tried to alleviate that in sort of in this work, the work that I talked about very quickly in the end, the MRI one, where we sort of had a part of the model that was trained for every case. So what the blind learning thing module does is it learns a dictionary on a case-by-case basis for every patient, for every slice that's being imaged, different dictionaries being learned. And that is complemented with a supervised network that was trained on a large data set. So maybe that kind of brings together these two flavors, where it's like, maybe the supervised network has population adaptive features, but it may miss out features that are specific to a new patient. But then this blind learning module may capture some of that, and that's in our paper as well. And so sort of they can complement, and so we don't have to necessarily to transfer learning of this big supervised network, which that has its own challenges as well.
All right, we have a question here, which looks like it's both for Maxime and for Sai. So I'm going to reword it a little bit so it kind of fits with both. So it says that many machine learning approaches are focused on qualitative questions versus quantitative feature extraction. So, can you comment on how machine learning is used for those two different cases, both in astronomy and in medical imaging?
Maybe I can go briefly and then Max can add in. I think like Nicole, you do a lot more quantitative use of machine learning for fingerprinting. I think in work that I've done, quantitative use of machine learning has been for like doing density reconstruction in CT or density reconstruction. Yeah, in CT, because in CT we can kind of get quantitative density reconstruction of materials forming the object. And so there we have used some amount of machine learning recently, but everything that I showed here in these slides were sort of qualitative reconstructions. We are not quantifying tissue properties or anything like that. It's just the visual features in the image that are being used. But I think, Nicole, you can add more on like the quantitative side with fingerprinting.
Yeah, I'd say Sai is right. We use it for both. I think, yeah, part of the question, and maybe this will make more sense for Max as well, is that there's like the qualitative application might be more like classification as opposed to like the quantitative brightness or detailed shape parameter extraction.
Exactly, that's what I wanted to say. Perhaps the biggest success of machine learning methods in astronomy is classification, because of course no one plans to look at billion galaxies by hand in any way. And this is qualitative anyway. So we just have some classes we not really well understand ourselves, and then basically we'll look at statistics of the results. However, people are trying to do quantitative analysis as well. I think scientists would always be skeptical if they can't assess uncertainties and things like that, which obviously machine learning methods are not the best known for. However, I think it's a big research domain and certainly is interesting area to continue. In imaging itself, well, if we can translate like our measurement into like very sparse domain, not like in the sense of scientific paper, but just a number of measurements where we actually want to extract from that domain, then potentially it is possible. We just get the answer, and then basically knowing the answer is half of the problem. Then we can try to quantify how good it is through some other ways.
In radio astronomy, dynamic ranges, which is the strongest source versus the weakest trustable source, is approaching 1 million, which is what, 60, 70 dB kind of a dynamic range. What are the dynamic ranges typically required and achievable from the noise coming from the measurement device itself in medical imaging?
So for CT, the dynamic range tends to be very large. And so often when we display the images, we are really doing a sort of a limited window display so that we can see the soft tissues. Otherwise, if we display it, we'll just see the bones, which have very high intensity. For MRI, that I think at least images that I've looked at, it's not as much an issue as for CT. I'm not sure if that answers the question.
Yeah, sort of answers the question. I was looking if there is a number I can carry in my head, like radio images, you can carry a number kind 70 dB kind of a dynamic ranges are not unheard of. What kind of dynamic ranges are in medical images? One of your slides had some number which was sort of 30 dB kind of number. Is that typical?
So in CT, we measure things like in Hounswell units, and then that can be, and sometimes we also offset so that 0 Hounswell units corresponds to like water or something like that, but it's not uncommon to have the intensities ranging to like 1,500 or so Hounswell units and so on in CT. Yeah. And I think in CT, the images are they are non-negative and they kind of make more sense. In MRI, these are complex valued images. So, I think they are a little bit more interesting to sort of to interpret the quantitative values of the, MRI of the MRI pixels.
Yeah, we don't really look at our images or think about them in dB, but I'd say that the dynamic range is definitely smaller than in radio astronomy. I think 30 dB probably makes some sense.
Said about dynamic range on CT goes from almost literally no counts hitting to detector to millions of hits on the detector. Okay, so that's a measure. Let's thank both our speakers for really excellent talks.